Thank you. I will begin. Dear Heavenly Father, we thank you for this day. I just pray that you'd help us to use this time wisely, just so we can wrap up questions that remain about the homework on energy and momentum. Lord, in your name I pray. Amen. Is it bouncing? You sure? Okay. Go ahead. What's your... bicycle problem on the bridge. I can try. Which number was that?
6 or 7. 7.
All right. Let's think through this here. You and your bicycle have a combined mass of 79 kilograms. When you reach the base of a bridge, you are traveling along the road at 7 meters per second. All right, the vertical height of the bridge is 5.1 meters. Your speed at the top is 1.5 meters per second. Ignore the work done by friction and any efficiency of the bike on your legs. What's the total work done on you and your bicycle when you go from the base to the top of the bridge? So you can just calculate the change in kinetic energy, right? Because the work energy theorem says that the work done is equal to the change in kinetic energy. I mean, that's a general result. We proved that independent of whether the force is conservative or not. So if we're asking what's the net work done, that's it. Oh, I'm going to have to leave that one off, I think. Otherwise, we won't be able to read the silly projector. So, I mean, that's what you do, right? I mean, so... so you do what? Excuse me. 1/2, 79. Your initial kinetic energy is what? The initial speed's 7, right? Meters per second. And then minus 1/2 of 79 times what's the final speed? 1.5. This will be in joules, and the answer's supposed to be in joules, right? And so whatever that is, yeah. So basically 79 over 2, which is 38. 38 times 49 minus 2.25, whatever that is. I'm sorry? Oh, 79 over 2 is, well, 38.5. Yeah, sorry. Thank you. Yeah? Is that right? Or is it 30? No, 39.5, right? I get approximately 1846.6 joules for mine, and in terms of sig figs, minus 1850. And the number is negative, right? Duh. Yeah. Wait a minute. Oh. What have I done? There's an error, right? This is the initial minus the final. So obviously, I have messed it up, right? It should be this plus that, right? Final minus initial, right? That's the change. So there's a minus out here I have somehow neglected. All right. So what's the how much work have you done? How much work have you done with the force you apply to the pedals? So how can someone tell me how to solve that?
Work equals the change in kinetic energy plus mgh.
No. Work is equal to the change in kinetic. I mean, work of what is the question? I think the real question here is what is the there's work done by what? This is the how much work have you done? How much work have you done with the force you apply to the pedals, right? I do think MGH has something to do with it. I think you're absolutely right. But why is, I mean, I think what you just said will give you the right answer. But why? Let's look at it this way. We have the work done by gravity, right? Plus the work done by you, right? What's that equal to? The net work, right? So what is the work done by gravity in this situation? It's equal to minus the change in potential energy. Right, which is, yeah. So let's see here, that should be PE final minus PE initial with a minus, right? In other words, PE initial minus PE final. What is PE initial? What's the initial potential energy? If we take H equal to 0 down here, right? It's 0. And what's the final potential energy? MGH, right? Now, okay, so that's actually equal to minus, what was it, 79. G is 9.8. And the H here is what? $5.1, okay. So what's the net minus negative change in potential energy? Minus the change in potential energy is actually this product, whatever it is. I get minus 3,948.4 joules. Now, what does that have to do? Well, the thing is, we're trying to find what? Right, we're trying to find this. We've just found out that that is minus 3,948. We already know that the network is minus 1,846, so we just have to add this to both sides. So what do we get? So work done by minus 1846 plus 3948.4 equals 2, whatever that is. $2,102.4. Yay, I can do physics. Okay, sorry. Sometimes I wonder. As you know, my terminal degree is in math. Yes, see. You got to show some work. I mean, if you don't show work and you just have the right number, then I don't give you much. So
So in this case, you added the, or I guess, yeah, you added the change
I
in
mean,
potential energy and then
the
change in
I'm sorry. Still processing his question. Hold that for a second. I mean, I don't. There's many steps here that you wouldn't have to write, right? But like the idea work done is equal to the change in kinetic energy. That should definitely be there. You know, that the net work is the sum of the work done by the gravity and the work done by this. That should definitely be there. The algebraic everything. I mean, no, I don't. I'm not too much of a stickler for those sorts of details. But if you don't write me enough that I know what you're doing, it's hard for me to give you partial credit if you're wrong. Anyway, I'm sorry, your question was?
You just did the change in potential energy plus the change in kinetic, essentially.
No, what I did was I used a result, which is that the work which is done by a conservative force, all right, is minus the change in the potential energy for that force. We derive this as follows. So the work done by a conservative force is equal to the integral of the conservative force dot dr, right? But that is minus the integral of the gradient of the potential function, whatever that potential function is, for the conservative force. Now that has to exist, right? If it's conservative, F is equal to minus the gradient of some potential energy function. But then by the fundamental theorem of calculus, this is minus phi of, Q minus phi of P, well, plus phi of P. Here I'm supposing that the curve goes from point P to point Q. And so you see what that is. Well, that's the change in potential energy over the curve, but with a minus. That has nothing to do with the net force. That's just a statement. If I just focus in on a conservative force and I want the energy, the change in energy, the work done by that conservative force, I can just calculate the change in the potential energy function for the conservative force. This will also be equal to the change in kinetic energy when the net force is conservative. But this is not a case where the net force is conservative, because there's like the pedal force, and then which is, coming from your internal kinetic energy, internal chemical energy, and blah, blah, blah. You're pedaling on the bike, you're doing work on the system. And that's part of this, so the net force is not conservative. Gravity is conservative though, because it's gravity. So that's why I can focus in on this part of the work, which is from the conservative force, and relate that to the change in potential energy.
I feel like it's a problem, like, he has to do the work in order to get the hill, but then he lost some speed, so you just kind of subtract away the work I guess he didn't have to do because he didn't maintain his speed.
I suppose that's an interpretation of it, but
I can't find my work on stuff to do exactly what I did.
You got the right answer?
Yeah, I got the answer.
Yeah.
Other problems too.
Sorry guys, I'm a little low energy today. I don't know. Odds I get stuck on something are pretty high here. Ask me about the easy problems first, please. Here, I'll get my laser out. I'll feel better if I have my laser out. So what you guys have? You have another question, I'm sure. Yeah. Third homework number. What is going on with this thing? Wait a minute. Third. Which homework?
That's homework number 8. My bad.
Momentum?
Yes.
And number 3 on that. Is that what you're saying? I can't get this thing off. Oh, man. Oh, no. This is very... Ooh, weird. I heard that. Sorry, I can't get this to be a pointer. All right, number 3. Engine of an orb. That's the one you're talking about, right? Okay, so the engine of an orbital maneuvering system, a space shuttle, exerts a force of 28,500 newtons for 4.6 seconds, exhausting a negligible mass of fuel relative to the 95,000 kilogram mass of the shuttle. What's the impulse of this force for, what is the impulse of the force for this 4.6 seconds? All right. So what's impulse, guys?
Force from changing time equaling to change in momentum.
When is that true, what he said?
When force, then that force is time.
Very good. Yeah. But more fundamentally, impulse is the change in momentum, right? Which is the integral of dp dt from whatever time interval we're talking about. But yes, that's just the force times the change in time if the force is constant. And since we're not told otherwise here, we should assume it's constant. So the impulse, I just take, 28,000, what is it, 500? What was the increment of time? 4.6 seconds. And that will give me that 1.31 times 10 to the 5th. And kilograms meters per second is the unit of momentum. That probably wasn't what you had a question about, was it? Oh, that was? Okay. What's the shuttle's change in momentum from this impulse? Oh, fine. There's a philosophy. The impulse is what the force does, and that produces and matching an equal change in momentum. Fine, whatever. Sorry, I'm not that nuanced in my terminology. You see what it's saying? It's like the impulse is due to the force, but that causes a change in momentum. That's the philosophy here, I suppose. But they're equal. The question? C, what's the shuttle's change in velocity from this impulse? Well, that's more interesting, right? So the change in momentum is equal to mass times the change in velocity, provided what? Yeah. They didn't pay me enough this semester to study the variable mass problem. Sorry, guys. So we'll just deal with constant mass problems. Hee hee. I'm just kidding. I just don't feel like it. All right, 1 over m. What is m?
95,000.
95,000, yes. The variable mass problem is more complicated. It really should be left to physics majors. All right. So I'll teach it to all the physics majors here. 1.31 times 10 to the 5th kilogram meters per second. And whatever that is. Yeah. 1.38 meters. Okay. I can also read the slide. Yes. And this I is what? I is a unit vector in the direction of the force, right? The impulse is in the direction of the force. The change in momentum is in the direction of the force. You know, the change in velocity is also in the direction of the force here. A good example of impulse being given to an object, of course, is like a baseball hitter, right? At the plate, he swings the ball. Swings the ball. I'm tempted to just turn off everything and walk away. I don't know. It's awful. I'm sorry. But he swings the bat, right? Oh. Like this, right? And then, oh, didn't really work. Well, hopefully the bat stays together. I guess I hit it. I need a yeah. Do you see that video of the guy catching the bat in front of his kid?
Yeah.
That was really something. Glad he got it. But anyway, of course, you know, you hit the ball, and then the impulse that the bat gives to the ball is in the direction the bat is swinging, right? And that's the same direction the change in momentum for the ball, right? And then the resulting change in velocity of the ball also that way. I mean, it all makes sense if you start thinking about that example. All right, you guys have other questions? This one, I think we're done with. Yep.
Homework 8, number 8.
Am I still on 8?
Yeah.
It has to do with like a bullet hitting a horizontal box with the friction of
Okay. Nope. I'm tired of grading. I think I'm going to make your next test just one page. No? Oh.
That means like 2 questions is going to be 150.
Yeah, would that would mean that, wouldn't it? I bet you'd be careful and show your work on those 2 problems, though, wouldn't you? Let's see here. 3-gram bullet. You're like, but showing work reveals what I do and do not know. It is a 2-edged sword. For the work that I show reveals my ignorance. Right? There's too much and there's too little. Somewhere in between, just the right amount of, you know, it's kind of like dating, right? But a 3-gram, I mean, you don't want her to find out who you really are. I mean, see it. I'm sorry. Is that, did they teach you that in psychology of relationships, or no? They teach nothing? They should have Dr. Sprano come in there one day and just be like, it'd be amazing. A 3-gram bullet is fired horizontally into a 2-kilogram wooden block resting on a horizontal surface. The coefficient of kinetic friction between the block and the surface is 0.15. The bullet remains embedded in the block, which is observed to slide 0.4 meters along the surface before stopping. What was the initial speed of the bullet? Oh, well, this isn't a bad one. Let's see here. So, I mean, here's the block, and here's the bullet. The bullet. What is the initial speed of the bullet?
That's what you're finding.
Oh, we don't know. This is requiring something known as algebra. And that's, 3 grams. Oh no, they're using grams. The mass of the bullet is 0.003 kilograms. K is for 1,000. 0.003 kilograms. 2-kilogram wooden block, which is initially at rest. What happens?
You hit it.
It hits it. Gets stuck in there. All right. This has many of the same ingredients as the problem where I lost half of my points on the test, right? Like, there's this initial hitting. Right now the bullet's in here. It has some initial speed v1, right? To get from here to here, we must conserve momentum. And then it skids along here, loses energy due to friction, right? Energy via friction, and then it stops, right? What's that distance? Oh, yeah, 0.4 meters. Change in x equals to 0.4 meters, right? Okay, so here's how we're going to do this problem. Number 1, we're going to conserve momentum as the bullet is embedded. Number 2, we are then going to assume that the initial kinetic energy is equal to the kinetic energy lost due to friction. Does that make sense? The initial kinetic energy of the block is exactly the same as the work done by friction. Okay. So, momentum conservation to start with. Mom. All right. See here, it's a MomCon. All right. What we got? 0.003 V naught is equal to 2.003, that's the mass afterwards, times V1. Oh, so therefore, V1 is equal to a certain proportion of V naught, I'll figure out that number, 0.003 divided by 2.003 is equal to 1.49778, actually 1.4978, I'll keep 5 numbers to be safe, times 10 to the minus 3 V naught. All right, then what? So the kinetic energy, 1/2 times 2.003 V1 squared is equal to what? It's equal to work done by friction, right? I'll say the magnitude of the work done by friction. Since the work done by friction is arguably negative, but I don't care about that minus, I just want the number. The number is, well, it's the normal force times force of friction, right? Times the change in x. Again, I just want the magnitude. I don't much care about the minus there. Which is what? mg mu delta x in this case. 2 kilograms plus 0.003 kilograms is 2.003 kilograms. That's the net mass after the bullet's embedded. So then what? This is 2.003 times 9.8 times what is mu? 0.15, all right. What's delta x? 0.4. Oh wow, they even let us so this is equal to V1 squared, right? I guess I can figure out this number. What is that number? I get 1.17776, whatever. So this gives me V1 squared is equal to, let's see here, that times 2 divided by 2.003. Funny. V1 squared is equal to basically 1.176 by my calculations. That's going to be in meters per second quantity squared. But we already know what V1 squared is this, right? I mean, V1's that, so I square that. So this gives me 1.4978 times 10 to the minus 3 quantity squared times V naught squared is equal to 1.176. So V naught is equal to 1.176 divided by 1.49 times 10, well, 1.4978 times 10 to the minus 3 quantity squared, square root of all this stuff, whatever that is. I get like the square root of 524,203. 724.0 meters per second. Oh, what do you know? Cool.
Professor,
Yeah.
after you calculated the work done by friction, what happened to the 1/2 and the mass? Why didn't you multiply that over to get V1 squared?
But I did. See, funny thing, this is so close to 1 that it's almost, this is a different number than that, but it's ever so slight, right? I changed it from 1.17776 to 1.76 because this number is if memory serves me correctly, that is his mother's ringtone. But
We'll have to ask when he comes back in.
you guys can ask him if you want. That reminds me, I have his homework. All right. So does that make sense, you guys? I mean, so basically, the things to keep in mind as you're working problems, if there's a collision, conserve momentum, right? If friction's involved, usually we can use just the force times distance formula to get the work done because friction isn't usually variable. So this is a nice problem. There's a lot in this problem, you know? There you go.
This homework too.
Can I erase? You got everything? Okay. Yeah, what's done is done. Which one?
The ice skater one, where the guy goes off at
Which number is that?
4 or 5?
Is this 8?
Pretty sure. Yeah, 5.
Right? 2 ice skaters, Daniel and Rebecca, are practicing. See if I can make this thing a little bit bigger. And then Daniel is an idiot. He stops to tie his shoelace, and while at rest is struck by Rebecca, who's also an idiot. Let's see here. Moving at 13.2 meters per second before she collides with him. After the collision, Rebecca has a velocity of 9.6 meters per second and an angle of 36.4 degrees from her initial direction. Both skaters move on the frictionless horizontal surface of the rink. What are the magnitude and directions of Daniel's velocity after the collision? Okay, now, so this is a good example of a problem where you get to define the coordinates, right? So what I suggest to us to start with is that Daniel, as will be described by this block, is sitting there, and then there's Rebecca over here, right? And she has an initial speed v naught of, what was it? 13.2 meters per second. Then, as I mentioned, there's a collision, and then after the collision, here's the direction that she was going to start with, okay? Basically, I'm just saying she's initially going in the x direction. Just define the x direction to be her initial direction, okay? What did we told? She collides with him, and after the collision, she has a velocity, a magnitude of 9.6 meters per second, angle 34 degrees. So Rebecca, she goes off like this. So, and her what's her speed? What do we with 9 point? I've forgotten already. 9.6. This angle, for some reason I remember, 36.4 degrees. All right. And then there's Daniel. We're trying to figure out what's the magnitude and direction of Daniel's velocity, right? So Daniel, I mean, you can see, I mean, I can set this up abstractly and allow for him to have an arbitrary velocity, but you can see from common sense here, he has to be going upward, right? Because the net momentum to start with is purely horizontal. The momentum is conserved in the collision, so he must be up here somewhere. Right, at some angle. We don't know that angle. Let's call it theta. And we know mass as well, right? So what's Rebecca's mass? 50 kilograms. What's Daniel's mass? 70.6 kilograms. Okay. So then you just conserve momentum, right? And we need to give a, let's say that Daniel has speed v, since I have not used v yet there. So the first thing to do with a problem like this is to draw a picture to try to make sure you understand what's going on. The second thing to do is to label the things you don't know. The third thing you do is you write down momentum conservation and or you use trigonometry. Think about vectors. So let's see here. Actually, I guess the fourth thing I'll do will be conserve movement. I'm gonna do the trigonometry first. So what's the initial momentum? Yeah, 50 times 13.2, 0, right? In other words, it's horizontal. That's the mass. What's the momentum of Daniel? Doesn't have any. That's right. Now over here, the final momentum is going to be equal to, well, mass of Rachel, which is 50. And then this one, this as a vector is what? I mean, you've got 9.6 cosine of 36 minus 9.6 sine of 36. 0.4, of course. Sorry, I can't. So let's see here, 9.6 cosine of 36.4 minus 9.6 times the sine of 36.4. And then plus what? Plus 70.6, right? And then I guess I can either do it in terms of v and theta, but it's probably easier just to say Vx and Vy here. Right. Of course, we know that we're going to have Vx is equal to V cosine theta, and Vy is equal to V sine theta after everything's done. But just as an intermediate, let's just talk about the velocity in terms of its Cartesian components. It might be easier. And this is added, right? Okay, so then momentum conservation. We have 50 times 13.2, comma 0 is equal to 50 times 9.6 times the cosine of 36.4 plus 70.6 times Vx, comma, minus 50 times 9.6 times the sine of 36.4 plus 70.6 Vy. Two equations, two unknowns, you can solve them. Let's see here. In particular, I have minus, I've got 0 from the y component. I have 0 is equal to minus 50 times 9.6 times the sine of 36.4 plus what? Plus 70.2 Vy. Is that right? Oh, 70.6 Vy. So that tells me Vy is equal to what? So it probably would have been easier to figure out this stupid number and not write all this stuff all the time, right? Or maybe to work with some letters would have been even easier. Oh well, it's too late. Whatever that is. Shoulder hurts. 70.6? It's funny. Oh, 70.6. Thank you. I get 4.035. Approximately. And let's see here, x, in the other hand, x, we have a non-zero component to start with. On the left-hand side, I've got 50 times 13.2 is equal to 50 times 9.6 times the cosine of 36.4.
Plus 70.6
Thank you.
dx.
Okay. So we get Vx is equal to what? Oh, I did something wrong. I got 600 something. No.
3.88.
What'd you get?
3.88.
3.88. Anybody else get that? 3.6. Nope, 3.88 wins. Sorry. Wait a minute, aren't you in? Isn't this you? Yeah. That's the mass of, what's the 13.2? That's the velocity of Rachel to start with. Okay, so now we know his, what's Daniel's velocity? As a Cartesian vector, it's what? It's 3.88 meters per second, comma, 4.035 meters per second. How do we figure out its magnitude and direction? Same way as usual, right? So that's squared plus 4.035 squared. And then I square root that. I get a magnitude. The speed is 5.595 meters per second. And the theta, I can use inverse tangent here because they're both positive, so inverse tangent works. I get 46.1. Okay. How would you calculate the change in kinetic energy? I'm not going to do that. But all you do is you calculate the kinetic energy of Rachel before, and then you calculate the kinetic energy of Rachel afterwards and the kinetic energy of Daniel afterwards, add them together, subtract that from this, and see what you got. That's the change in kinetic energy. Yeah. Kinetic energy depends on the speed. So all you need for the 5.59, yeah.
I kept getting v sub y as a negative, right? Why did you not get a negative?
Maybe you didn't put this negative over here?
Mine's negative as well.
It's I had like the momentum in the beginning one equal the momentum in the end, and then you have Vx and Vy on one side. That's the only things you don't know. So I move everything over to the other side. And when you do that, you have to subtract the y component, but there's no y component initially, so then it's just zero.
I mean, I don't know what to tell you. I mean, as I have the coordinates set up, this is a negative, and that's what makes this positive.
Did you set the coordinates differently?
Did you make Rachel go above the dotted line?
I did, and I got negative y.
Then that switches a minus to the other thing. Yeah. I mean, you could turn it over, and you'd be describing the same problem. We don't disagree. We just chose different coordinates. Let's say it another way. There's two different physical problems that have the same start as the problem we have.
My final answer is a negative angle, so just like grab some values around the tangent thing.
Right. Well, clockwise from Rebecca's original direction of motion. Well, you got a negative angle, but that's counterclockwise. So that's why you had to drop the minus.
I guess it can be used as a reference.
Yeah.
If you need to use a minus, but just one
Yeah.
angle.
Yeah, it's subtle. I just happened to avoid all that by drawing the picture this way. That wasn't on purpose. I just got lucky. Other questions? Yes? Same one? I'm going to try to be less detailed in my response from the last 20 minutes. Two ice skaters. You just said number 4, didn't you? One of James Bond's adversaries is standing on a frozen lake. There is no friction between his feet and the ice. He throws a steel-lined hat with a velocity of 28 meters per second at 36.9 meters above the horizontal, hoping to hit James. If the adversary's mass is 140 kilograms and that of his hat is 9 kilograms, what's the magnitude of his horizontal recoil velocity? Interesting. Well, why can't you? If he had just thrown it horizontally, then yeah, I think you. But that's the thing that makes it slightly tricky. Is he throws the hat. So, I think the vertical part of the motion must be dealt with by like his knees and the recoiling of his body, whereas the horizontal recoil is just absorbed into horizontal motion on the lake. So so this was 36.9, right? So the question is, what's the conserve momentum in x direction, all right? So before and after. Before, 0. Right, he's just standing there before he throws his hat. That's it. Afterwards, you have the mass. What's his mass? 140. And then his velocity, let's say v. All right? I allow that v could be positive or negative, of course. It's one-dimensional. So, basically, after he throws the hat, I can see already that his velocity is going to be like that, right? The hat is airborne. It's off this way, right? I mean, actually, part of the velocity is vertical, but we don't care about that. We're focusing here on the right after it's thrown. The horizontal momentum is what? Nine kilograms, right? Times the cosine of 36.9 degrees, right? Times the speed of the hat. What's the speed of the hat? 28? 20, is it 28? Right, that's the speed of the hat, right? So that says to me then his horizontal speed is like minus 9 times 28 times the cosine of 36.9 divided by 140 meters per second, of course, given everything else I've done. One 1.4394. Yep. So V minus 1.44 meters per second. Which makes sense with my setup. Of course, what does the WebAssign do? It asks you for the magnitude. So there you go. That minus tells us the direction, but we don't care. Yep. Number 3 on homework 9. By the way, what's the x momentum of the hat as time goes on until it hits James Bond, let's say? Oh, wait a minute. Don't want to do that. I think I was just looking at Mr. Omby's homework. That's no good. It's what? It's constant, right? Why is it constant? There's no air resistance. Yeah, we're assuming that because gravity does not do work on the hat, right? In the x direction. There's no force, there's no impulse delivered to the hat, so it just continues on as it does with its x momentum being whatever it was to start with. Although we did not actually find that number. Come on. Come on. You can do it. You can do it. You can't do it. All right, fine. Where are we? Homework 9. Which one? Math. Phooey. A discus thrower applies a force, like so, to a discus with a mass of 1.93 kilograms, where alpha and beta are constants and gamma is another constant, which are given. If the discus was originally at rest, what is the velocity after the force has acted for 0.497 seconds? Express your answer in terms of I and j unit vectors. So I think this is really just a F equals ma problem, right? So to solve this, what I would do is I would say, okay, so F is equal to the mass times dv dt, right? I believe that this force is the net force on the discus. Yes. And he's applying the force from time 0 to time 0.497 seconds. So I suppose, I guess what they want you to, well, they tell you the mass? It did, yeah. Well, tell you what, I'll find a way to make this about. Let me find a way to make this about. This is dp dt, right? Which is also mdv dt. I don't know. I don't really think this is absolutely a Chapter 9 problem necessarily. I mean, you could look at it as a Chapter 9 problem, but you could just as well look at it as a Chapter 3 problem. The point here is that if we integrate, so, you know, we have what? We have f dt. I can divide by m, right? That's equal to dv. If I integrate this from, say, time 0 to time 0.146, what is it? 467? 497. Well, and I integrate this from, say, the velocity at time 0 to the velocity that we're interested in. Then I have the velocity of 0.497 seconds minus the velocity at time 0, which, by the way, is given to be 0. So this integral will give me the answer. So all you got to do is integrate that force, right? You have to integrate 1 over, what is the mass? 1.93. Be careful, are the constants all given in kilograms, meters, and seconds? Yup. Or newtons and such. And then, I mean, you got yourself an alpha t squared. And you got yourself a beta plus gamma t. So that's going to be equal to the speed you're looking for. Let's work it out. Other questions?
Is there a way of doing that without doing integrals?
No.
By doing that by the x and y of momentum?
I don't think so. This is a variable force.
Is it a variable force?
Well, yes. It's got a time dependence, so the t squared, the gamma t term. I guess to make this more Chapter 8 or 9-y, I would say calculate the impulse delivered by the force. That's how this problem would be changed to make it more interesting on your test, for example. You know. But yeah, if the force is variable, we just have to integrate. I mean, that's always there. We haven't integrated up till now today because we've been working with stuff where we already did the integral, like potential energy, right? Or the force has been constant over the displacement, so we can just select the component of the force which is in the direction of the displacement and then multiply by distance, and that's it. But that is a special case, right? If the force is variable, we have to integrate to find the work done. Other questions? It must be time. No, it's not time. You still have 9 minutes. You guys are messing with me. I mean, we can stop here if you want. It's up to you.
Can you do the problem 1 on this homework?
Today? Maybe. At one instant, yes. At one instant, the center of mass, At one instant, the center of mass of a system of 2 particles is located at the x-axis at x equals to 2 meters and has a velocity of 6 meters per second in the x direction. One of the particles is at the origin. The other particle has a mass of 0.2 kilograms and is at rest on the x-axis at 14 meters. What is the mass of the particle at the origin? What is the total momentum of the system? What is the velocity of the particle at the origin? Yes. Okay. Let us draw a picture.